It's my great pleasure to present our good friend and very good researcher, Professor Zhirayr Avetisyan. He will present a talk titled Mixed-Fourier-norm spaces and holomorphic functions. And we are very happy, Zhirayr, that you agreed to deliver a talk at our seminar. And please, thank you and go ahead.
Yeah, thank you very much, Alexey, for the kind introduction. First of all, I would like to express my gratitude towards the organizers of this series of seminars for this opportunity to present our recent work to your attention. So indeed, today I want to talk about mixed Fourier-norm spaces and holomorphic functions. This is a joint work with Alexey Karapetyants, whom all of you know very well. So here is the structure. First, I'll begin with a motivating example, essentially the unit disk. And we'll look at what is well known on the unit disk, and we'll try to dig a bit deeper to see what the idea is on this example. And then we'll take that idea, separate it, generalize to make a general scheme. And then we'll have some abstract results on the general scheme, which will be valid on certain model cases, model geometrical settings. And then we'll see how, given a problem, given a setting, we'll use so-called a kind of canonical holomorphic coordinates to translate our problem to one of the model situations, apply the general result in the model situation, and then carry back this entire structure to our original setting. So there will be this push forward, pull back kind of setting. So after presenting this general scheme, we'll come back to examples. First, we'll revisit the original unit disk, but we'll look at it from a different perspective. We'll try to recognize on this familiar example the abstract objects that we defined in the general scheme. And then we'll go to the less trivial example, the hyperbolic half space or a unit disk, on which we'll again apply this general scheme and see how it works and what it translates to when you come back to the original coordinates. Some of you in the audience have probably heard this talk before, so sorry for any repetition. Hopefully, this time I'll add a couple of new insights anyway. All right, so we begin with this motivation. So we have the unit disk, D, which we consider as a set of complex numbers, W. Well, actually, we'll begin with the punctured unit disk. We'll see that it is the punctured unit disk that's the natural domain of our constructions, especially because we're going to use the polar coordinates. So R is the radial coordinate with ranges from 0 to 1, 0 not included, and that's why it's the punctured disk. Phi is the radial variable, it ranges on the unit circle. And so the domain is the punctured disk, and the origin is kind of a point of a boundary. And as usual in complex analysis, interesting things happening at the origin. We'll talk about this a little later on several occasions. So now suppose I have a function f, which is defined on this unit disk, which I can regard as a function of two variables, the angular variable phi and the radial variable r. For every fixed r, I can perform a Fourier transform, say sufficiently regular function. I perform a Fourier transform with respect to this angular variable phi. And the result is another function, phi hat, which is now a function of an integer n and the radial variable r. So from the perspective of a two-variable function, this is kind of a half Fourier transform because we perform Fourier transform only with respect to one variable, and the other variable just stays aside. So this is kind of an angular Fourier transform. It is performed for every fixed R. So, and then we can use the inverse Fourier transform, or the Fourier series in this case, to reconstruct the original function f from its half Fourier transform. All right. So now, as I said, we're going to discuss analytic functions, holomorphic functions. So the Cauchy-Riemann operator, which is d by dw bar, if the w bar is the complex variable adapted to the standard complex structure, then d by dw bar is the Cauchy-Riemann operator. I can rewrite it in these polar coordinates, and it has the following form, the first displayed formula on this page. And the condition of analyticity is that d by dw bar of f is 0 in a neighborhood, right? So if I rewrite this in polar coordinates, I get this PDE, the second line, second displayed formula. And now if I perform a Fourier transform with respect to the variable phi, and what I get is actually an ODE. I get an ODE, which I can solve easily. The solution is written in the bottom right corner. So is the thing. And then if I plug this back, into the Fourier series, I'll find what? I'll find that f phi of r equals this. Here I already substituted fn r to the n. And then I just get what? Fn times this quantity to the n, which is basically the Laurent series for a function analytic in the punctured disk, right? So nothing new, essentially undergraduate complex analysis stuff. But now we are looking at it from a different perspective. Basically, what we are saying here is that the condition of analyticity is reflected in a certain factorization of the half Fourier transform into a radial part and a Fourier part. And the radial dependence is fixed by analyticity. You see, f hat at n comma r equals some coefficient f of n times r to the n. The r dependence is fixed. The arbitrariness of this analytical function f is now encoded solely in this coefficients fn. And this idea we're going to take and generalize. Okay, but now let's look at the origin. As I said, we have here a Laurent series because the condition of analyticity, the Cauchy-Riemann equations, we applied only in the punctured disk. So what happens at the origin? As we all know, the Hertog's theorem and many other multidimensional analogs, of course, Morera's theorem and so on in complex analysis. If you have an isolated singularity or an isolated point, a function holomorphic in a neighborhood of an isolated singularity is holomorphic, including the point, if and only if it is bounded there. So this basically means f is holomorphic in the whole disk, including the origin, if the supremum in a neighborhood of 0, in a neighborhood of the origin of the function is finite. It's bounded in a neighborhood of this boundary point, boundary from the perspective of the punctured disk. On the other hand, we also know that a meromorphic function given by Laurent expansion is holomorphic if and only if only the non-negative index coefficients in the Laurent expansion are present. which means it is basically Taylor expansion, right? So I write it in the following way. I say that the support of this coefficients Fn, the support of the Fourier transform is in the non-negative integers. So in this familiar situation in the unit disk, these things are equivalent. So it's holomorphic at the origin if it is bounded and if the support of the function of the Fourier transform is in the non-negative real line or non-negative integers. In larger generality, in our general scheme, there won't be such equivalence, but there will be one-sided implications, but we'll see it later on. All right. So what is the general scheme? We begin with G being an abelian Lie group. Usually it is connected, but never mind for the moment. And Y is a general smooth connected manifold. We consider test functions on G Cartesian product Y, G cross Y. These are not any standard test functions. These are neither Schwartz functions nor the standard compactly supported functions. It is a mixture. So this is essentially the space of test functions which are of rapid decay in the group directions, so to speak, and of compact support in the other, in the irrelevant, so to speak, directions. Mathematically, this is basically the tensor product of the Schwartz space on the group and the test function space on the manifold. So this exists, of course, by nuclearity and so on. There is this abstract functional analysis behind it, but actually in the paper, we have written down explicitly and carefully all the semi-norms and everything. So all computations are done from scratch in an explicit manner. No magic here. Accordingly, the distributions are the dual space, the members of the dual space of this test function space, which can be again seen as a tensor product of tempered distributions on the group and the standard distributions on the manifold. But again, here we describe this semi-norms giving the topology of distributions again in explicit terms and everything. So it's written really in all details. All right, so, and then we define what we call the half Fourier transform, which basically takes a test function and performs a Fourier transform in the first group variable only. We know very well how to perform a Fourier transform of a function living on an abelian Lie group, right? So we do that, but regarding the extra variable as a constant. In other words, this is first defined as component-wise operator acting by Fourier transform on the Schwartz space and trivially on this test function space, and then extend it to the full tensor product by continuity. Or we can write it down in the integral form, the f hat, the third displayed formula, f hat of xi y is simply the Fourier transform of f x y with respect to the variable x. So you replace x by xi and y stays as it was. It is the irrelevant variable. And then, as usual, the Fourier transform of distributions is defined by duality starting from the test functions. All right. Then once you have test functions, you are also interested in the multiplier algebra of those test functions. What is the natural algebra of functions, smooth functions, by which you can multiply test functions and get back your same test functions? And the same for distributions. Of course, these things are well known since the seminal work of Laurent Schwartz and so on for standard distributions, but here we have non-standard distributions. So we have to do some of these things from scratch. We describe these multipliers. they are nothing else but smooth functions which are of tempered growth, polynomial growth, so to speak, in the group directions, and of arbitrary growth in y directions, basically a mixture again of the standard multipliers. And we prove from scratch the continuity of this product. By the way, this is component-wise continuity. It is well known, well understood that even in the case of standard distributions and tempered distributions, this multiplication operator, operation of multiplication between multipliers and test functions is not jointly continuous. It is only continuous in each variable separately, and this is maybe one good, naturally occurring, non-artificial example of a component-wise continuous, non-jointly continuous function for your students. Okay, so then similarly, we construct this multiplication operator for the distributions with the same algebra of multipliers. Then we consider the invariant differential operators. Well, G invariant. G is a group that acts on this product manifold in the obvious way. It translates the first component and leaves invariant the second one, right? And all operators on this product, G cross Y, which are invariant with respect to this action, are called G invariant. You can think of them as differential operators with smooth coefficients not depending on the group coordinates, depending only on the Y coordinate, not depending on X. And finally, the G moderate differential operators are, well, formally, this is the algebra of differential operators generated by the invariant operators and the multipliers considered as zero-ordered operators. Technically, this is the algebra of operators of which the coefficients are of moderate growth in the group directions and of arbitrary growth in the irrelevant directions. All right, so now let's talk about measures and measurable functions on this space. You can easily show that any G invariant Radon measure on G cross Y is essentially the product of the H measure on G and a certain measure on Y, which I call d nu. For the purpose of this work, since we are working on manifolds, we'll be interested in smooth measures. So this d nu will be a top form, a volume form on Y. And then correspondingly on the Fourier side, there will be another measure, again, G invariant. Well, G hat invariant, because the dual of an abelian Lie group is again an abelian Lie group. So, and this invariant measure is simply d psi times d nu, the same d nu, but d psi is now a H measure on the dual group. All Lebesgue spaces LP here will be considered with respect to one fixed invariant measure mu. Okay, now the main objects of the construction come in. So we begin with relatively arbitrary, and by relatively arbitrary, I mean there are some very mild conditions like a lattice property for the norm or so, pretty mild conditions for the Banach spaces. So there is this curly Y Banach space of distributions on the manifold Y. So the Banach space is continuously embedded in the space of distributions. This is not very strong. It's easy to satisfy. And then we take another Banach space of tempered distributions, essentially Banach space which is continuously embedded into the tempered distributions on the dual space G hat, but we want it to consist of locally integrable functions considered as distributions. So you see, we have a little bit more liberty in choosing the Banach space on the manifold Y, because we are not going to do much with it, but we're going to perform Fourier analysis with the G component. So we are a bit more strict about distributions on G hat. We require them to be locally integrable functions, actually, but taken with the topology of tempered distributions. All right, so the first main object is this mixed norm space, which is essentially the space of all locally integrable functions on G hat taking values in the Banach space curly Y, integrable in the sense of Bochner, of course, such that the pointwise norm evaluation, which is now a scalar valued function G hat, belongs to our original Banach space Xi G hat. And we take a norm. The norm of this U hat is defined to be the Xi norm of this pointwise evaluation scalar function. Okay. Now, again, under some reasonable assumptions, these are very basic things, like, again, like some kind of inequalities, lattice properties, and so on, which are almost always satisfied. This becomes a normed vector space embedded continuously in the space of our distributions on G hat cross Y. So may I remind you again that G hat is exactly, again, an abelian Lie group. So whatever we said about G cross Y applies equally well to G hat cross Y, all these constructions. Okay. So we get that this mixed norm space is actually a normed vector space. And the big question is whether this is actually a Banach space. And the answer is, unfortunately, we don't know. So at this generality, we are yet unable to prove that this space is complete. I have to say that because the idea behind this work, the situation with the unit disk, actually originates from some earlier work by Alexey and some of his co-authors. And in the particular case of the unit disk, and with further restrictions on this Banach spaces, that they are both embedded in L1 spaces on corresponding manifolds, and the Y is taken to be the 0-1 interval. So very special classical situation of the unit disk. They were able to prove that this mixed norm space is complete. Okay, so there are grounds to believe that this might be the case also in general. It is just that we are unable to find a proof as of yet. All right. Now we had the mixed norm space. Now we have the Mixed-Fourier-norm space, which is essentially the Fourier pre-image of the mixed norm space. In other words, our Mixed-Fourier-norm space chi over G cross Y is the space of all distributions U, of which the half Fourier transform belongs to the mixed norm space defined in the previous page. And we take the same norm as that of the Fourier transform. So essentially, this makes the half Fourier transform an isometric isomorphism of normed vector spaces from the mixed Fourier norm space to the mixed norm space. So again, because we don't know if the mixed norm space is complete, then equivalently, we don't know whether this mixed Fourier norm is complete. The same question here, so it's equivalent. Right, now if we want to discuss holomorphic or analytic functions on this product, this model situation G cross Y, we need some complex structure. And as a complex structure, we take the most natural one. Well, if G is just an abstract Lie group as a manifold, then you can think of this as what is called the almost analytic continuation of G. But because G is actually an abelian Lie group, it is an algebraic group, and it is embedded in an algebraic manifold. It has a natural algebraic extension to complex numbers. It's just what you think, nothing fancy. We just take Y to be an open subset of Rn and have the same dimensions as G, and take Z to be X plus IY. Basically, G plus I times Y is our complex manifold structure. Now, the first principal result of this work is the following fact, this displayed formula. That remember that on the unit disk, we saw that the analyticity of the function f was reflected in a certain factorization of its angular Fourier transform, and the R dependence was fixed. Here we have a generalization of that. So a distribution on G cross Y is holomorphic with respect to this complex structure if and only if its half Fourier transform factorizes in the following way. The Y dependence, the dependence upon the coordinate in the irrelevant direction, is fixed. It is this e to the minus 2 pi psi y scalar product. And the arbitrariness of the holomorphic function u is purely encoded in this psi dependence of u naught hat. So this is exactly the generalization of what we had before. If you think of coordinate transformation, if you replace r by e to the minus 2 pi y, look at the last line, then you simply recover the formula we had for the unit disk. So again, the analyticity or holomorphicity of a distribution is encoded in a factorization property of the half Fourier transform, wherein the Y dependence is absolutely fixed and explicitly given. Now, some intermediate constructions, technical constructions, before we proceed. Of course, for every fixed psi, this function e to the minus 2 pi scalar product with psi is a distribution on the manifold Y. And we take the Y norm of this distribution if the distribution falls outside of the Banach space curly Y, then we just set it to be plus infinity. That way, we get a certain weight function, which we call rho psi. And then there are some technical, of course, assumptions needed to make sure this function is measurable and so on and so forth. But bear with me, this is only a presentation. The details are all presented in the paper if you are interested. So then with this weight, assuming it's measurable, we construct the weighted space psi. So we had pretty arbitrarily chosen our favorite space of distributions on the dual space psi g hat. Now we make a weighted version of it in the following way. This collects all possible locally integrable functions u naught hat, so that its absolute value multiplied by rho falls into this Banach space psi. And then we equip this space with the norm as given in the last displayed formula, namely the psi norm of this product of the weight and the absolute value of u naught hat. So again, under some reasonable mild assumptions, with this norm, actually this weighted space is complete. We show that it is, so it is a Banach space. Right. Now, what we do is we look at the holomorphic functions inside the mixed Fourier norm space. Okay, so we have this mixed Fourier norm space Xi on G cross Y, and we select only those members of these distributions which are actually holomorphic functions on G cross Y, and we call it curly A Xi. Well, we'd like to call it the Bergman space for reasons that in the unit disk, this is actually the Bergman space of holomorphic functions. Right. Now, the next principal result of this work is this proposition that under certain mild assumption, as always, as ever, the half Fourier transform gives you an isometric isomorphism of Banach spaces between this subspace of holomorphic functions among the mixed Fourier norm space members and elements of the following form. This known factor e to the minus 2 pi times scalar product times this Banach space of this weighted Banach space, or more precisely, this map that takes distribution U to its half Fourier transform, namely e to the minus 2 pi Xi y times U naught Xi, is actually an isometric isomorphism of Banach spaces. One particular kind of implication of this is that, remember that we proved that Xi G hat rho, this weighted space, was complete. It's a Banach space. This proposition then indirectly proves that although the full mixed Fourier norm space wasn't proven to be complete at this generality, but the subspace consisting of holomorphic such elements is complete. So this gives you a Banach space Xi of holomorphic elements in the mixed Fourier norm space, and it immediately gives you a nice parametrization of holomorphic elements among mixed Fourier norm space elements in terms of its half Fourier transform, because it's just parameterized in a bijective way by the elements of this normed space, this weighted Banach space Xi on G hat. All right, now, as I said before, these were some model cases. This is an idealized situation where we have a product manifold. You have the group G and then a manifold Y. You already work in canonical coordinates, so to speak. But often what you begin with is a slightly different setting. You don't know the canonical coordinates yet. You begin with some complex manifold omega, and then you have some group action, an abelian Lie group acting analytically on this manifold. Then you are looking at what is called the principal stratum. What is the principal stratum in the theory of group actions? The principal stratum is the subset of the domain consisting of orbits of highest dimension, or orbits of smallest stabilizer subgroup, which is equivalent. So we are looking at the orbits of this G action and choosing those orbits which have the highest dimension. They are called generic orbits. And the union of all generic orbits is usually an open dense subset under certain regularity considerations. It is called the principal stratum. We look at this open subset, open dense subset, consisting of highest dimensional generic orbits. Then we find holomorphic coordinates that map this subset into the standard coordinates. In other words, we find the G equivariant biholomorphism, capital Phi, from the model G cross Y to our actual domain that we have at hand. So here we'll assume that Y is in an open subset of the positive quadrant of Rn. And you know why this is the case? Because we want to go back to what we discussed before. Remember that in the very beginning, we said holomorphicity at the origin of the disk, which was a boundary point for the punctured disk, was equivalent to boundedness of the function around that point, or to a Pay-Levine kind of property that the Fourier transform is supported in the non-negative half part. So we want to have something like that here. That's why we choose Y to be in a positive octant, so that we give sense to such Pay-Levine properties on the next page. Namely, under certain mild assumptions, we get that for every element of this analytic space Xi, basically every holomorphic distribution, the support of the half Fourier transform is indeed the intersection of G hat with this positive non-negative octant, 0 plus infinity to the end. So every holomorphic function has this Pay-Levine support property. Not the other way around necessarily. And the next one regarding boundedness, again under certain mild assumptions, for every element of this holomorphic mixed Fourier-norm space, the distribution is actually bounded outside of a certain strip beginning with the vertical coordinate y0. So there exists a y0 so that for every y1 larger than y0, the supremum of u further than y in the positive directions is finite. So this is an analog of boundedness around the origin for the unit disk. All right. So this was the general scheme. Now let's come to examples. As I promised, the first example will be again the unit disk, but now we'll look at it from a different perspective, trying to recognize our abstract objects in this familiar situation. So we take the unit disk with the so-called elliptic geometry. In this case, our complex domain omega is exactly the unit disk itself, the full unit disk. The group is the unit circle. G is simply T, the one-dimensional torus. And then the model space is G. So the group action of G on the domain on D is given by this complex multiplication. So for every X in the unit circle, the multiplication or the action of the X element on the W point is given by this rotation W times e to the 2 pi I X. So basically G acts by rotation. It shifts the angular variable but leaves the radial variable. Now from this vantage point, you can already see why the origin is not naturally in the domain. Because if you look at the orbits of this rotation, all orbits are circles except the origin. The circles have dimension 1. They are generic orbits. The center the origin has dimension 0, it is an exceptional or singular orbit. So it is not part of the generic of the principal stratum. It's not the generic orbit. So that's why it is the punctured disk that's more natural from this group actions perspective. So from the Fourier transform perspective, the punctured disk is the natural object. It is the principal stratum, D minus the 0 point. And the Y manifold is simply R plus. Here, the model. Now, what is the change of coordinates that takes us from the punctured unit disk to the model? First of all, the group is T, and the Y is R plus. So our phi maps from T cross R plus to the punctured disk. And it has an explicit formula. This is basically phi z equals e to the 2 pi z, all r times e to the 2 pi I x. Anyway, so this is this biholomorphism that maps from the model to the punctured unit disk. Now, it is important to look at the boundaries. What happens to the boundaries in this change of coordinates? When W approaches the boundary of the disk, the unit circle, then in the model space, we are basically approaching Y equals 0. If you think of the model space as a cylinder, a half cylinder, half infinite cylinder, beginning from 0 and going to plus infinity in its axial direction, then approaching the unit circle, the boundary of the unit disk, in the translated realm means approaching this 0, one end of the cylinder, this cutting part of the cylinder. Whereas when W approaches to the origin, then Z approaches to the other, the infinite end of the cylinder. Okay, so this means that whatever we had, like this Paley-Wiener properties and boundedness and so on, this analyticity, subtleties around the origin for the unit disk, in the model space, they are translated into statements at plus I infinity, at the infinite edge of the cylinder. Okay, so we will be looking at that part as the right asymptotic region for Paley-Wiener type properties. All right, to continue, of course, the dual of the circle group is the integer group, G hat is Z. And then for simplicity, we take the Banach space Xi, simply a small LQ space, and the Banach space curly Y as a certain arbitrary function space on the Y, which is now R plus, the positive half plane, half line. And what we do, so we translate functions from the model to our original domain. So essentially, if we had a test function, now because our group is compact, the T is compact, Schwartz space on the group consists simply of smooth functions. They are all compactly supported automatically. So the test functions in this case coincides with compactly supported functions on this product manifold. And when translated to the original disk coordinates, then you are dealing with functions f, which are compactly supported in the punctured disk. And our half Fourier transform now is simply the usual angular Fourier transform, as you can see. Then we introduce this X Banach space on the last line as the pullback of this chosen space on Y. So we translate this 0, 1 interval into the R plus with the exponential mapping and so on. So now the mixed norm space, the mixed norm space is this space, well, mixed Fourier norm space is this space curly L QX of D, which is simply the push forward of the mixed Fourier norm space on the model space T cross R plus. More explicitly, what it becomes, it is the space of all distributions in the punctured disk such that this norm is finite, and this norm is a typical mixed norm, as you can see. So our mixed Fourier norm, when specialized to the unit disk, really gives to what earlier author considered as mixed norms on the unit disk. So it's a sum over the Fourier variable xi of Banach norms taken to the power q, and then the sum is taken to the power 1 over q. So the Bergman space is then the intersection with functions holomorphic in the punctured disk. So it consists of all holomorphic functions in the punctured disk, which, when half Fourier translated, become such products f xi r to the xi. Remember that xi belongs to the integer, so it's basically n, such that this mixed norm is finite. So this gives you an explicit characterization of holomorphic mixed Fourier norm functions. All right, now, as I said, less trivial example is the half plane with the hyperbolic geometry. Now, in this case, the domain omega is the half plane, upper half plane, C plus or capital pi or whatever. The group is the real line, the real numbers, and it acts by dilations. So every element x of R, the group, acts on the complex point W by stretching it in radial directions. You basically multiply it by e to the x. These are stretching or dilations from the origin towards the infinity. Now, as you can imagine here, all orbits are straight lines emanating from the origin and going towards infinity. They are all one-dimensional. All orbits of the group action are of the same dimension. They are generic. So essentially, the principal stratum is the entire domain. There are no extra boundary points. And then the irrelevant variable is the angular one going from 0 to pi. This basically parameterizes the rays emanating from the origin in the half plane. Okay. So thus, our model G cross Y is here R cross 0 pi, and the holomorphic coordinates map this model space to our half plane. So the model space is essentially a belt, right, of thickness pi around the real axis, whereas the domain is the half plane. And the explicit form of this holomorphic transformation is this. So phi of z is e to the z, basically the exponential map. Now, again, it is important to look at what is happening at the boundaries in this transformation. So when W goes to the boundary of this half plane except the origin, then essentially in the model, you are looking at either of the boundaries of this belt, horizontal belt, okay? Either the lower boundary or the upper boundary. When you are approaching the origin, then in the model, you are going to minus infinity along the belt in the horizontal direction. And when W goes to infinity in radial directions, then you are going essentially to plus infinity in the model. You have the belt, you go to the right infinity horizontally. Okay. So this basically translates the singularity problems from your original situation to the model problem. Right, here the dual of R is again R, so G hat is R again. For simplicity, you can take the Lebesgue spaces LQ on G hat. And again, the Y, curly Y space can be pretty arbitrary, any function space on this Y manifold 0 pi. Here, this translation from functions on the model to functions on the original domain or the other way around has to be taken in a careful way. Well, not has to be, it's just that when we do it this way, then we get good things. You can do it in another way, you'll get equivalent things which are nastier but still equivalent. Okay. So if we take this T lambda for any lambda larger than -1, you take this transformation T lambda, it translates functions on the domain to functions on the model, and it has the following beautiful property that it translates the Fourier transform to Mellin transform. Okay, so essentially you have this radial. If you think of e to the minus y 1 plus lambda half as the radial variable R, then in your model, if you take the radial variable R and perform a Mellin transform with respect to the radial variable, in the model, you are basically doing our standard half Fourier transform. So whatever properties you have proven for the model case with respect to the Fourier transform apply to Mellin transform in this hyperbolic geometry. Right. More precisely, the mixed Fourier-norm space now becomes, by definition, the pullback of the mixed Fourier-norm space on the model, but precisely this is simply the space of all distributions on the half plane, of which the following norm is finite. The norm is again a typical mixed norm. Okay, so you have an LQ norm, a Q norm of the pointwise norm evaluation of the half Fourier transform, half Mellin transform. So if you translate it to your original coordinates, then you are basically writing in terms of Mellin transform. Now coming to the Bergman space, which is basically picking up the holomorphic elements from this mixed Fourier-norm space. It consists of all functions holomorphic in the half plane, such that the Mellin transform factorizes in the following way. There is this there is this obvious y dependence which is fixed again, and this f naught psi, and this f naught psi is such that this norm is finite, and the norm is given explicitly in terms of this f naught. Okay, because this factor e to the minus 2 pi psi y, it can be computed explicitly for given Banach norms, and you have just a normed vector space. You can explicitly compute these norms, and then the Bergman space is characterized by its Mellin transform belonging to an explicitly given weighted Banach space. All right. Okay, so I guess this is all I was planning to share with you today. So all of this can be found in this preprint. So yeah, as I said, this is a joint work with Alexey Karapetyants. It's well, possible applications go into things like the symbols of Toeplitz operators and so on. The kind of contexts where the original mixed Fourier norm spaces have appeared in their work on the unit disk, but now we have a much wider choice of possibilities, essentially of geometrical settings where we can try to apply these things. All right, thank you very much for your attention. That's all for today.
Well, thank you, Maria. Thank you very much, Zhirayr, for very nice presentation. And we have time for questions, please, if any. Was the question or what?
Nothing.
Okay. Meanwhile, I have some maybe comment, Zhirayr. We actually have application in our paper in mathematical notes together with you regarding application to Toeplitz operators in these spaces.
Right. So we have a recent paper where Toeplitz operators on this standard hyperbolic spaces are considered, where the results from this paper are also used.
Yes.
That's right.
Yes. Yes, correctly. And I also wanted to note that all this study appeared in as an answer to the issue that, for instance, if you have a standard Gilbert space that you are done, you have many tools, you have so many good features like Pelley-Wiener theorem, like parsimonic equality, etc. And once you just go from L2 to LP, you lose almost everything of this nice tools. And the study that we have done with Zhirayr was an answer how to define spaces to preserve such nice tools, to have ability to use kind of extension of Pelley-Wiener type results. And it was done in very good generality of in this paper. Well, maybe some more questions. I don't see hands. I guess it was very detailed talk, so no questions left. Well, if no questions, then let us thank speaker for very nice presentation. Thank you, Professor Zhirayr Avetisyan, for very nice presentation.
The pleasure was all mine.
Thanks to everyone.